Question 1 gives us this stationary wave. It tells us that it's at the point when the particles have their greatest displacement, so in other words they don't get any further away from the zero line than they are here, and it tells us that the period is 0.04 seconds. So the first thing it wants to know then is what the wave's going to look like after 0.01 seconds. So the point is that 0.01 seconds is equal to t over 4. In other words, it's gone through a quarter of the time period. Now if you remember what happens as a stationary wave oscillates, if this is the maximum displacement, it will go down to there, and then down to there, and then back up to there, and then back up to there. So that's a quarter of a time period, that's a half, that's 3/4, and that's a full time period to take it back to where it started. So after a quarter of a time period, which is 0.01 seconds, this point is going to have reached here, and indeed every point in that arc between there and there will have reached 0, and every point between there and there will have been travelling upwards and will have reached 0. So after a quarter of a cycle it's actually dead flat across the middle there. Okay, so that's the one that we're going to label B, okay, because it's dead flat after a quarter of a cycle. Now 0.02 seconds is half a cycle, okay, because it's half of 0.04. So that means that all of these points will have moved down to their sort of mirror image positions around there. So this point will have reached down to there. So what we'll then get is a wave that looks like a sort of reflection of this. So it's going to look like this. Oh, I can't draw very well. Okay, that one should obviously come all the way down to there. Right, so that's our wave after half a time period. So we're going to label that one curve C. And then we have to label the nodes and the antinodes. So remember, node, you can remember, is no displacement. So nodes are the point where nothing happens. Those points just always stay on the 0 line. So that is a node down there, and an antinode is where you get the maximum displacement from the 0 line. So that, for example, is an antinode. Okay, then we have to describe the motion of the particle at V, giving frequency and amplitude. So V is down here. So the first thing to describe the motion is to make it clear that V just oscillates vertically up and down. Okay, it's not moving from side to side in any way. So we just get that V oscillates vertically up and down, but that's kind of implied by what we said, but that is an important thing to get across. And its amplitude is the maximum displacement it achieves from the 0 line. And that's obviously 20 millimeters, because we're told that it's at its greatest displacement in the original curve that was drawn. And then it wants the frequency. So frequency is how many of these cycles it will complete in a second, and that's just given by 1 over the time period in seconds. So it's just 1 over t, which is 1 over 0.04. Okay, because 0.04 was the time period that we were given, which is 25, and that will be because this is seconds, that would be seconds to the -1, but remember that that unit is actually the hertz. The reciprocal second is a hertz, so 25 seconds is the frequency. In part C, it asks us first of all for what's the amplitude of the motion of the particle at W, and you can see that again we know that this is its maximum displacement, and then it's just going to oscillate by going down to there and then down to there and then back up and then back up. So its amplitude is its maximum displacement, and it never gets further than the 10 millimeters it's at the moment. So for particle W, the amplitude is 10 millimeters. And then it wants to know about the phase relationship between W and Z and W and V. So it's very important here not to get confused between stationary waves and travelling waves, because in a stationary wave, remember that the wave just oscillates up and down, it's not travelling in either direction. So what that means is that between any two nodes, so between here and here, all of the points in that arc reach their maximum displacement at the same time, and then they all reach 0 at the same time, and then they all reach their maximum negative displacement at the same time. In other words, they're all moving exactly in parallel with one another, but just with different amplitudes. So all of the points within that arc have the same phase, they're all in phase, and the phase difference is 0. So we say that W and Z are in phase, okay, meaning they're at the same point in their oscillation cycle. In other words, the phase difference is 0. But W and V are antiphase. Those are exactly out of phase, because when W reaches its maximum displacement, maximum positive displacement, V is at its maximum negative displacement, and vice versa. So they're exactly out of phase. So the phase difference, and if we express this in terms of radians, the phase difference is equal to pi radians. So in question 2 we have this situation where we have two speakers both transmitting sound at the same frequency, and we have the sound travelling over this distance, and then these are points in space along that line, and it's sort of basically saying that if you stand at point C, you hear a maximum in the intensity of the sound, but if you stand at E or D, you hear a minimum. So the question is why? And what you have to think about here is the distance the sound has to travel. So if we focus on what's happening at point C to start with, which is what it asks us first, why is there a maximum at C? The important thing to realise is that that's the path length from the speaker to C, and this is the path length from the other speaker to C, and because C is at the midpoint here, those two path lengths are the same. Okay, so to explain why there's a maximum at C, the most important thing to say is that the path length the sound has to travel from the speaker to reach point C is the same for both speakers. So same path length to C from both speakers. So why does this matter? Well, in the end you just have to learn the answer to that, but if we just want to try to understand this a little bit, let's just do that. So remember, we're talking about sound waves here, so the longitudinal waves, which are difficult to draw, but we can sort of draw it like that to represent here. Remember, where the particles are squashed together is a compression, and here where they're more spread out is a rarefaction. Now that's kind of painful to draw, but if we just use a sort of shorthand representation and say, right, so let's mark this point where they're maximally compressed, like that, as the wave goes along, and then this point where they're maximally rarefied, like that, and then like this again. Then we could say, right, if we think about what's happening from those two speakers, so here's one path length and here's the other, then you can see that what's going to happen is if they both start, for example, with a compression like that, then because the wavelength is the same for both, and because they're both in phase at the beginning, then where this has a rarefaction, so too does this one, and when this one has a compression, so too does this one, and therefore wherever they are when they reach that point, they're in phase, and that means that you'll get superposition. Remember, when two waves meet, you always get superposition, which means the waves add up together, and if they're in phase, that produces constructive interference, which means that the displacement is increased because they add up together and give you a bigger displacement than you would have had from each wave individually. And so that's what's happening there. So if two path lengths are the same, or if they differ by a whole number of wavelengths, then when they arrive at the same point, you'll get constructive interference. On the other hand, if they're half a wavelength apart, then you'll get destructive interference, and then you'll get a minimum in displacement at that point. So let's get that written down then. So maximum at C means the same path length to both speakers, and that means that sound waves which are in phase when formed at the loudspeakers, and they would be in phase if they're broadcasting the same sound, you know, from the same amplifier, if you like, formed when formed by the loudspeakers, will still be in phase when they meet, which means that superposition of these waves, which is what happens when the waves meet, produces constructive interference. And that means an increased amplitude, which means louder sound. Okay, so that's the story. That the important things that you need to get in there is, first of all, that this is only true because they have the same path length. So the sound waves which are in phase when formed by the speakers will still be in phase when they meet, and then you need to have this word superposition in there, which is just the general statement that when two waves meet, the displacement simply add up together, and that's what superposition means. And superposition of in-phase waves produces constructive interference, which means that it increases the amplitude. So you need to have that idea of constructive interference in there as well. And then you can just explain that means bigger amplitude and therefore a louder sound. So next, in part D, we have to explain why we, at certain points along here, which have been labelled D and E, you get a minimum in the intensity of the sound. So again, we can think of this in terms of interference effects. So again, here we've got two longitudinal waves, and you can see this is a wavelength. Okay, is the distance between one compression and the next or if you like between one rarefaction and the next will be the same distance. And you can see that this is a wave which is 180 degrees pi radians out of phase. So it's an anti-phase wave because you've got a compression here, you've got a rarefaction there, we've got a rarefaction there, you've got a compression here, rarefaction there. So this is an anti-phase wave. And you can see that that situation is going to arise if the distance travelled by the wave differs by half a wavelength or an odd multiple of half wavelengths. If it multiplies by a whole wavelength, if it differs by a whole wavelength, then you can see that this is just going to move on to there. So the compressions will be in the same place. But if they differ by half a wavelength or an odd number of half wavelengths, then you're going to get this situation where when they meet and they superpose, a compression is superposed on a rarefaction and they will just add up to 0. And the same at all these points, compression on rarefaction, and so on. So you get destructive interference. So your explanation is that the path lengths from the two speakers to E or D differ by half a wavelength. Or an odd number of half wavelengths. However, the way it's described here is that moving from C to E, you don't pass through any other maximum or a minimum. So this is the first minimum that you arrive at. So we don't really need this proviso of an odd number of half wavelengths. There will be further maxima and minima out here, but if it just says it decreases, then we can just remove that proviso and say, right, it differs by half a wavelength when it reaches E or D, which means that the waves are antiphase when they meet. So superposition produces destructive interference, which gives decreased amplitude and therefore quieter sound. Okay, so really all you have to do is remember that it's about the path length, and if the path length differs by a whole wavelength or any multiple of a whole wavelength, you know, whole number multiple of a whole wavelength, then you'll get constructive interference. But if it differs by a half wavelength or 1.5 or 2.5 or 3.5, then you get destructive interference. B asks us to calculate the wavelength of the sound, so we start with this relationship that C, which is the speed, is equal to the frequency times the wavelength, so that's on your data sheet, and therefore trivially we can rearrange that to get that lambda is equal to C over F, and then we can just literally plug the numbers in. So we've got C is 330 meters per second divided by F is 2000 hertz, which is 2000 number of hertz seconds to the -1. So the answer will just come out in meters, as it should, and that comes to 0.165 meters is the wavelength. Now, in order to calculate the distance between C and E, which is what it asks us to do next, you need to use this relationship, which is again on your data sheet, which is that W is equal to lambda d over S. And you need, that's on your data sheet, but you need to remember what those various terms mean. So W is the distance between adjacent maxima or minima So if we were talking about light, it would be the distance between the centres of two bright fringes or the centres of two dark fringes, because it's the same number. In this case, it's going to be the distance between two maxima of the sound intensity or two minima of the sound intensity. So that's what W means. D is this distance. Okay, so it's the distance, the if you like, the perpendicular distance between the line where the sources are and the line where the fringes are being detected. So it's 5 meters in this case. And S is the separation of the slits. So D is 5 meters because it's that perpendicular distance from the midpoint of the two sources to the center of the interference pattern that you get. It's easier to see what it is than to put it in words, but it's that. And S is the separation of the sources, which is 0.75 meters. So although that expression is on your data sheet, it's very easy to not remember what those three things W, D and S are, so make sure that you know what that expression means. Once you've got that, it's quite easy, because we get that W will be equal to lambda, which is 0.165, times D, which is 5.0, divided by the spacing of the sources, which is 0.75, and if you calculate that, it comes to 1.1 meters. However, that's not the answer to the question, because that's the distance between adjacent maxima or adjacent minima. In other words, it's that distance, and CE is therefore only half of that distance. So CE, which is the distance from maximum to minimum, will be equal to 1.1 over 2, so just half of that distance, which is 0.55 meters. Okay, so it's easy to fall at the final hurdle of that. It's the usual thing, like, calculating the radius but needing the diameter. It's those things you've really got to constantly watch out for. So it's that factor of 2 there. Who's the Labrador of choice? Is anybody feeling like walking him this afternoon, or shall I do that later?
I'm going for a run in a minute now, but I'll do it tomorrow, or I think we should have a big family walk tomorrow before the snipers are sent out.
Okay. Is either of you two going to do it, or shall I do it later?
I did it yesterday, Michael. No, I can do it, that's fine.
Can you? Thank you.